What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Review Exercises. Let's do it. So for this one, it says determine whether this represents exponential growth or exponential decay. Now, it is one of the two. It's not neither in this case, because we got a constant raised to an exponent, and there's that nice constant in front, which is the initial value. So the question is this decay or growth? Now, because this value in the parentheses that's being raised to the variable, that is between 0 and 1, right? So 0.825 is less than 1, greater than 0. Because of that, this is going to be exponential decay. That's how you do it. Done. For number 3, it says find an exponential equation that passes through these 2 points, so let's do it. We know we're starting with this baseline, and the way we can figure this out is we can plug in this value, right, for x, this for y, and this one as well, and create a little system of equations. So here we have 2 equations. Now, I plugged in the coordinates here and here. Now I'm going to isolate a in this first equation by dividing by b squared. And then I know that a equals 2.25 times or over b squared. Now I can plug this in for a down here. So there's the 2.25 over b squared, subbing in for a, and then times b to the 5th. Now, b to the 5th, and that's over b squared. That's going to subtract with the exponents, so that's going to be b cubed. Then we're going to divide by 2.25 to solve for b. And when you run that in a calculator, it's b cubed equals 27. Take the cube root of both sides to figure out what b is, and the cube root of 27 is 3, right? 3 times 3 times 3 is 27. So if b is 3, we can now solve for a using either of these equations. Let's plug it into, I don't know, the bottom one just for fun. So we got 3 to the 5th. So what is that? 3 to the 3rd, we already said is 27, times 3 again is 81, times 3 again is 243. That's b to the 5th. And then last but not least, we'll divide both sides by 243. And we get a equals 0.25. So now for our final equation, we get y equals a, which is 0.25, times b, which we got 3 to the x. So there's your equation, done. A retirement account is opened with an initial deposit of $8,500 and this amount of interest compounded monthly. What will the account be worth in 20 years? So let's get our compounded interest formula. So it's A equals my principal, which is the initial deposit, $8,500 times 1 plus the interest in decimal format, which is 0.0812 over the amount of times we're compounding per year, which is monthly, that's 12 times per year. And then to the nt power, n is the amount of times we're compounding per year, which is 12. And then to the t power, which represents years. But in this case, they tell us that that's 20. So now we got this great equation that we can plug and chug in the calculator. So let's do that now. So here we go. We plugged everything in as is, and this is the value we get. We get $42,888.18. We're rounding to hundreds because it's money. So we got 42,888.18. Boom. So for this one, the question is, does it represent continuous growth, continuous decay, or neither? Now, this is in the format of either continuous growth or decay. It's one of the two. And the way that we can identify this as decay is because this value up here, that exponent constant in front of t, is negative. So that means this is decay. Boom. Done. So for this one, we're meant to graph the function and then state the domain and range and give the y-intercept. So let's do that now. So we're going to start by stating the domain, and the domain's great because it's going to be for an exponential all real numbers, okay, which is negative infinity to infinity. There's no restriction. Now, when we talk about the range is going to have a restriction. Since there's no constant here, what we can tell is that this will never go below 0, right? It will approach 0, but it will never hit 0. So that means my range is everything from 0 up to infinity. Last but not least, to get the y-intercept, when we have a nice exponential, it's literally this constant. But to see that, you plug in 0 for x, 2 to the 0 is 1, 1 times 3.5 is 3.5. So the y-intercept is 0, 3.5. Now, if we want to plot this, we got a couple nice points. We got 0, 3.5 right here. If we plug in 1, we get 2 to the 1, which is 2 times 3.5 is 7. And then maybe negative 1, right? 2 to the negative 1 is 1/2 times 3.5 is 1.75. And as we mentioned, the range is at 0 and up, which means we have a nice horizontal asymptote at y equals 0. So now we can kind of plot the points together, connect the dots, and you see that it's going to go up and up and up to the right. It's going to hug that horizontal asymptote of basically the x-axis as we go to the left. That's how you do it. Done. So this says the graph of f of x is reflected about the y-axis and then stretched vertically by a factor of 7. So we need to find this new equation. So first, when we're reflecting about the y-axis, that means we're applying a negative directly to the x. So it's going to be 6.5 to the negative x. Then we stretch vertically by a factor of 7. That means we multiply the entire function by 7. So this would be our g of x. So now if we're talking about the y-intercept, domain, and range, let's start with the domain. Again, the domain, there's not going to be any restrictions. I can plug in whatever I want for x. So that's going to be negative infinity to infinity. Now, what about the range? This is never going to go to a negative, right? It's a positive to an exponential value. So even when x gets really, really big, it's going to approach 0, and x gets really, really negative, this is going to approach infinity. So the range is from 0, but it'll never hit 0, and then going to infinity, and this is just an interval notation, right? And then for the y-intercept, it's the value when x equals 0. So when x equals 0, it's 6.5 to the 0, which is 1, times 7 is 7. So that's our y-intercept, 0, 7. That's how you do it. Done. So to convert this to an equivalent exponential equation, we follow the process of taking the base, which is 17, raising it to the power that's on the other side of the equal sign, which is x, and setting it equal to this argument, which is 4913. So that's how you do it. Boom, done. So for this one, it's a to the negative 2/5 equals b. To write it as an equivalent logarithmic function, it's log, and the base of the log is this value. What's on the other side of the equal sign is that exponent, which is negative 2/5. And then what's over here, that becomes the argument of this logarithm. So the way we'd write it is log base a of b equals negative 2/5. That's how you do it. Done. So for this one, we're going to convert it to the exponential form and then solve. So the way we can do that is, again, it's the base 64 to this power that's on the other side of the equal sign, and that equals x. And now we have something pretty straightforward, right? X is the cubic root of 64. That's the same as raising to the 1/3 power. So what is the cubic root of 64? It's 4, because 4 times 4 times 4 is 64. So that's how you do it. Done. So to evaluate this one without using a calculator, I'm going to convert it to its exponential equivalent. And this log is really log base 10. So what this is saying is 10 to what power equals that argument, which is 0.000001. Now, I'm going to write this actually as a fraction. I think it's going to be easier because 0.000001 is 1/millionth, okay? So now I can say 10 to what power is 1/1,000,000th. And really, it's like saying 10 to what power is a million? Well, that's 6. But since it's 1/1,000,000, it's -6, right? Because a negative exponent means it drops to the denominator. 10 to the 6 is a million. So that gives us our value of -6 for x. Boom, done. For this one, to evaluate without using a calculator is pretty cool because we can use the logarithmic property that says if we're taking natural log of something raised to something, we're allowed to bring that exponent down as a coefficient. So now we have negative 0.8648 times ln of e. And the beauty of this is ln of e is 1, because if I take the log of a number and the base is the same as that number and natural log has a base of e, then that evaluates to 1 regardless. So that means our final answer when we evaluate this is negative 0.8648. Boom, done. So for this one, we're going to start by factoring a 7 out of that internal argument. So it's going to be log of 7 times x plus 3 and then minus 4. So the first thing I'm going to do is I'm going to try and figure out when we can get this argument equal to 1, because log of 1 is always 0. So we're going to set 7x plus 21, this whole thing equal to 1. So subtract 21 from both sides. 7x equals negative 20. Divide by 7, we get x equals negative 20 over 7, which is pretty close to negative 3. Now, this is cool because that's when this goes to 0. 0 minus 4 is negative 4. So we have one coordinate at negative 20 over 7, comma negative 4. And that's like right about here. I also know that I can't get less than negative 3. I can't even get negative 3 because that would give me log of 0, which is not allowed, right? We can't take 0 or negative numbers as an argument of log. So that's our vertical asymptote is going to occur at x equals negative 3. Another point we can plug in might be 0. We'd get 0 plus 3 is 3. Then that's log of 21 minus 4. That's approximately negative 2.68. So there we have a couple points, and this is enough to get a decent graph where we know it's going to go off to the right. It's going to keep going up even though it looks very gradual. And then as we go to the left, we kind of come here, and then we bring it down and we hug that vertical asymptote like so. So that's how you create the graph. Boom, done. So for this one, we're starting with the domain, then vertical asymptote, and end behavior of the function. So when we talk about the vertical asymptote, it occurs when this is going to go to 0, right? Because that's a no-no. We can't take a logarithm, natural logarithm, or any logarithm of 0 or any negative numbers. So that means 4x plus 20 has to be greater than 0. And then we can solve by subtracting 20 and then divide both sides by 4. So we get a nice domain of x is greater than negative 5. And that means the vertical asymptote is at that barrier, that boundary, x equals negative 5. And then when we talk about the end behavior, we're talking about two things. We're talking about as x approaches the vertical asymptote, and then also as x goes off to infinity, right, to the right-hand side. So since this is a typical logarithmic function, it's going to look like this, right? And here's the vertical asymptote. So as x approaches negative 5, you can see that it's going down, meaning the function value g of x is going to approach negative infinity. And then as we go to the right, as x approaches positive infinity, we can see the function value rising, meaning g of x is approaching positive infinity. Oh, and by the way, I forgot one quick thing. This needs to be a plus here because it's not approaching 5 from both sides. It's only approaching it from the right-hand side, and that plus indicates that we're coming from the right? The function doesn't exist on the left-hand side. So just a quick clarification. But anyways, that's how you do it. Boom, done. So for this one, we're meant to condense everything. And the cool thing is we can use the property of logarithms such that when the bases are all the same and they're all being added, we can just consolidate into one logarithm base 8 as the product of all of these arguments. So it's x times 5 times y times 13. So 5 and 13, of course, become 65. And then we have xy like so with log base 8 of this entire argument. That's how you do it. Done. So for this one, as we put it in compact form, we can use the property such that when logarithms are minusing, we can turn it into fractions, right? So first we have ln of z minus ln of x. So that's going to be literally z over x. And then we're minusing ln of y. So how does this play in? Again, now it's this minusing this. So we're dividing by y. So if this thing is dividing by y, it becomes ln of z still on top over x, and the y goes on the denominator. So it's natural log of z divided by x times y. Boom, done. So for this one, it says rewrite negative log base y of 1/12 as a single logarithm. So what we're going to do is we're going to take this negative coefficient and raise it up as the exponent of this argument, which is negative 1. So it's really log of y of 1/12 to the negative 1 power. But what is this to the negative 1 power? It means the reciprocal, which is basically log base y of 12, and that's how you do it. Boom, done. So for this one, it says use properties of logarithms to expand this. So let's do that now. First things first, I have 2b times this radical, so I can split it up into 2b and then plus ln of that, because when the arguments are multiplying, you can split it up as addition with the two separate arguments. Now, because these are multiplying, I can also break that up as addition, right? Ln of 2 plus ln of b. And then this I can actually break up as a radical of the numerator, b plus 1, over a separate radical of the denominator, b minus 1. Now I have division happening. And when I have division, that's the same as subtraction. So I can split this up into ln of rad b plus 1 minus ln of rad b minus 1. Now these radicals are really exponents, okay? So again, to the square root of something is raising that to the 1/2 power. So both of these can be rewritten like this. Then using my power rule for logarithms, I can bring this down as a coefficient for both. And since they both have a 1/2, I can kind of factor it out and say 1/2 times ln of b plus 1 minus ln of b minus 1, like so. And then that's the same as just dividing both of these by 2. And I'm only saying that because that's how they wrote it in the back of the book. So the final answer, again, we can't forget the ln2 plus lnb, like so. But the final answer as they wrote it is ln2 plus lnb. And then instead of writing 1/2, they just wrote as everything divided by 2, which of course is the same thing. ln of b plus 1 plus minus ln of b minus 1. And there's your final answer. Done. Condense the expression to a single logarithm. So the first nice thing that I see here is I've got everything is log base 7. So that's going to be cool. Now, the first thing I'm going to do is I'm going to take these coefficients and turn them into powers, which we're allowed to do with our properties of logarithms. So let's do that first. And that dividing by 3 is really a 1/3. So, multiplication. So I'm going to write this like this, and then I can do the same thing, right? That 1/3 can be raised as an exponent. and we'll do that next. But remember, raising something to the 1/3 is like taking the cubic root, so I'll write it like that. Now the last step, let's consolidate. So since these are adding, that will be v cubed times w6 for the argument. Since this is subtracting, this argument goes on the denominator, and then we consolidate everything to just be log base 7 of this argument, and that's the final consolidation. Done. So first we're meant to rewrite this as a logarithm, then apply the change of base to solve for x, so let's give it a shot. So first we're starting with log base 5, that's, this value here, to this power of this value, which is on the other side of the equal sign, equal to the exponent, which is 12x minus 17. Okay, so now we got this, and then it says to apply the change of base formula, which you can do to this. You can make it into a common log of the big number, the argument 125 over log of 5. So we could now plug this into a calculator. But the thing is, you actually can evaluate this as is, because this is asking the question, 5 to what power is 125? And that's to the 3rd power. But you could plug this into your calculator as the common log, and you'll see you get 3 as well. So now we get 3 equals 12x minus 17. Now we're going to add 17 to both sides to isolate. 12x equals 3 plus 17, which is 20. Last step, divide both sides by 12. And we get 20 over 12 is x, which reduces to, divide top and bottom by 4. 5 over 3 for the win. Boom, done. So for this one, we're going to start by having a common base for everything. And with 125, 625, and 5, they can all be expressed as powers of 5, right? 125 is 5 to the 3rd. And 625 is actually 5 to the 4th, which is pretty cool, right? So it's 1 over 5 to the 4th to the negative x minus 3. And this equals 5 to the 3rd. 1 over 5 to the 4th can be rewritten as 5 to the negative 4th, right? So that's really 5 to the negative 4th, and all of this to the negative x minus 3. And now we can multiply against this floating exponent here by distributing. So I get 5 cubed over 5, negative 4 times negative x is positive 4x, and then negative 4 times negative 3 is positive 12. And now we got this. This is pretty cool because now I can use my exponent rules where if I have the same base, I can just subtract the exponents on the left-hand side. So I get 5 to the 3 minus 4x minus 12, right? I'm subtracting that entire thing, equals 5 to the 3rd. Now I have 5 to something equals 5 to something, which means I can pretty much wipe out those bases and just say 3 minus 4x minus 12 equals 3. Now we'll do 3 minus 12, which is negative 9. And then we're going to add 9 to both sides as we isolate. Negative 4x equals 12. Last step, we divide both sides by negative 4. And we get x equals negative 3. Boom, done. So for this one, we're going to use logarithms to find this exact solution. So first things first, I'm going to isolate this variable, the n, by adding 1 to or subtracting 1, I should say, from both sides, which equals negative 61. Then I'm going to divide by 3. So I got e to the 6n minus 2 equals negative 61 thirds. Now, when we get to this point, we have to bring that exponential variable down. And the way we do that is by taking a logarithm of both sides. And since I have a nice base of e, I'm going to use natural log just because it's the easiest. But we got to stop right here and see that we're taking a log of a negative value. That's outside the domain of a logarithm, which means this is not going to fly. We're not going to get a viable solution, which means there's actually no solution here, or they want us to write explicitly no solution. So that's how you do it. Boom, done. So for this one, we're going to start by trying to isolate this x. So first, I'm going to add 9 to both sides. So that negative 56 plus 9 is negative 47. Then I'm going to divide both sides by 2, and I get e to the 5x minus 2 equals negative 23.5. Now, at this point, I need to bring this variable down, and we're going to do that by taking the natural log of both sides. But the issue is, in order to solve for x here, we're trying to take a natural log of a negative. That's outside of the domain of a natural log. I can't take negatives. I can't take a log of 0. So I already know this is a no solution situation. There's not going to be a value of x that will satisfy this. So no solution, or we can write it as no solution like this. There's your answer. Done. So for this one, we got a little quadratic in disguise. So I'm going to treat this, it's almost like if it was x squared minus x minus 110, okay? So how would I factor this? I would say what two numbers multiply to negative 110 add to negative 1? That'd be negative 11 and positive 10. And then instead of putting x and x here like a typical quadratic, it's what two values multiply together and give us e to the 2x. Well, that's e to the x, right? So now I got this nicely factored, and now I got two equations for this because I'm trying to figure out when this is going to go to 0. So I can look at each of these individually. When is e to the x minus 11 going to equal 0? And when is e to the x plus 10 going to equal 0. Now I solve. So first I'm going to add 11 for this one to both sides. And then to solve for x, I'm going to take the natural log. We need a logarithm to bring this x down as a coefficient. So then it's x times ln of e. And the nice thing about ln of e is it's 1. So x equals natural logarithm of 11. And it said exact answer, so we don't actually need to plug this in and approximate. This is one of the solutions. Now for the second one, we're going to start by subtracting 10 from both sides. But here, when we take logarithm here to solve for x, right? Again, we're taking a log of a negative value. That's not viable. That's a no solution situation. So this is not going to yield a viable solution. So this did. That's the only viable solution. Boom, done. So here we're going to use the definition of a logarithm to find the exact solution for this equation. So I'm going to start by isolating a. We're going to divide or subtract both sides by 9. So I got 6 ln a plus 3 equals 33 minus 9, which is 24. So now I'm going to divide both sides by 6 like so, and I get ln of a plus 3 equals 4. Now I'm going to convert it to its exponential equivalent, knowing that ln is really log base e. So we take that base, we raise it to this power on the other side of the equal sign and set it equal to the argument of the natural log, which is a plus 3. Last but not least, we're going to subtract 3 from both sides, and we get a equals e to the 4th minus 3. And we're not going to get an approximation. They want the exact solution, so this is it. Done. So for this one, the first thing I'm going to do on the left-hand side is I'm going to consolidate, because I know when I have logarithms that are the same base and I'm adding, it's like multiplying the arguments. So I get ln 5 times 5x squared, which is 25x squared, and then 5 times negative 5 is negative 25 equals ln of 56. And the one-to-one property says that we can now just set these two arguments equal to each other because I got natural log, natural log. Now once we get here, I'm going to add 25 to both sides and do our typical isolation. So we get 25x squared equals 81. Then we're going to divide by 25 like so. And then I got x squared equals 81 over 25. Last step, we're going to take the square root of both sides. And I get x equals plus or minus square root of 81 is 9, square root of 25 is 5. So we got these two solutions. Now, we want to check that both of these are viable. But the beauty of this original equation is that the x is squared. And there's only an x squared. There's no x, which means the negative and the positive, since they're the same, will give you the same value because you're squaring both of them. They're both going to end up being positive. So both of these are viable solutions. Done. So for this question, it says, how long will it take for the population to reach 1 million? Meaning we're solving for t when p equals 1 million. So let's plug and chug. So we're going to start by dividing both sides by 256,114. So this will cancel out, and we get e to the 0.25 t equals this crazy thing. Now to bring this exponent down and solve for it, we want to take log of both sides. I'm choosing natural log because we got this nice base of e here. That's going to allow me to bring this exponent down as an argument, which is 0.25t times ln of e. But the beauty of ln of e is it's just 1. So this equals natural log of this. And then last step, we're going to isolate by dividing both sides by 0.25. So let's plug it into Desmos and see what we get. And we get rounded to the nearest hundredth, 5.45. So t is approximately 5.45, and it says measured in years. So we'll say years. That's how you do it. Done. Find the inverse of the function of this logarithmic function. So the first step to finding the inverse is I'm going to rewrite that f of x with y. Then we're going to swap the x's and the y's like so. And then we're going to isolate the y. So first I'm going to divide by 0.25, which is the same as multiplying by 4. So I got 4x equals log base 2 of y cubed plus 1. Now, the cool thing is if we're trying to isolate, the easiest step here is to convert this from logarithmic to exponential, which means we're taking the base 2 to this, which is on the opposite side of the equal sign. So 2 to the 4x equals that argument of y cubed plus 1. Now we're just going to finish by isolating y, so I'm going to subtract 1 from both sides. And then last step, we're going to take the cubic root of both sides, which is going to kill that cube, and then we got the cubic root of 2 to the 4x minus 1. And then finally, we're going to rewrite this with that nice function notation, f inverse of x equals the cubic root of 2 to the 4x minus 1. Boom. So this question says to write an exponential model representing the amount of drug remaining after t hours. So it's based on this scenario where we start with 300 milligrams that decays by this much. So we're starting with f as a function of t, where t is time and time is going to be in hours. And then we start with our initial value, which is 300 times the decay rate, which is 1 minus 0.17, right? That's 1 minus this in decimal format, which is 0.83, and then it's to the t power, right? And then now if we're trying to figure this out, how much would remain at 24 hours, this is what we plug in for t, so let's do that in Desmos. So as we plug in, rounding to the nearest hundredth, we get 3.43, so we get 3.43 grams remaining, boom, done. So for this one, we first need the answer to 56, which says use Newton's law of cooling to write a formula that models the situation, and then we can plug in 85. So the way to do that is to write this out as the temperature equals the temperature of the room, which is 71, and then we add this to the difference of the initial temperature and the ambient temperature. So 350 minus 71 is 279, and then it's times e to the kt. So the first thing is we have to figure out what this k value is, and the way we do that is with this value, and it's saying at 15 minutes. So the temperature is at 175 when t is 15. So we can use this to solve for k. So I'm going to subtract 71 from both sides, and we get 104 equals 279 e to the 15k. Then I'm going to divide by 279, and then I get e to the 15k equals 104 over 279. Then I need to bring this exponent down. So I'm going to take a logarithm, and I'm going to choose natural log of both sides because we got e here. That allows me to bring this exponent down as a coefficient, and then times ln of e. Ln of e is 1. That's nice. So then we simply get 15k equals ln of 104 over 279. And then the last step is we're going to divide both sides by 15, like so. And this is my k value. And this approximates to negative 0.0658. So now we have t equals 279 e to the negative 0.0658. That's just an approximation times my t value and then plus 71. So now we got a great equation, and using this equation we're going to solve 57, which is how long will it take to cool to 85. So I'm going to plug in 85 and solve for little t. So we got 85 equals 279 e to the negative 0.0658 t plus 71. So now we're going to have to do some algebra. So we're going to subtract 71 from both sides first, and I get 14 equals 279 e to the negative 0.065. Then we're going to divide both sides by 279. So now we're writing down here, we got this equals e to the negative 0.0658 t. Then we're going to take the natural log of both sides because we need to bring that variable in the exponent down, right? And that's great because it brings it down, and then again, ln of e is just 1. So now I have ln of 14 over 279 equals to negative 0.0658 t. Last step, we're going to divide by negative 0.0658. And I'm going to do this in Desmos because we're going to get an approximation. And we're getting 45.47, which will round to the nearest minute to 45 minutes. So our answer is approximately 45 minutes. Boom, done. So for this one, it says, how many days will it be before the rumor spreads to half the carrying capacity? So the first question is, what is the carrying capacity? It's that numerator, 1200. So what's half of that? That's 600. So when is n going to be 600? So now we got this nice equation. We got to solve for little t. So first I'm going to multiply both sides by that denominator. So on the right-hand side, I get 1200, right? And then on the left-hand side, I get 600 times 1 plus 199 e to the negative 0.625t. Then we're going to divide both sides by 600. 1200 divided by 600 is just 2. Then we're going to subtract 1 from both sides, and I get 199 e equals negative 0.625t equal to 1. And then I'm going to divide both sides by 199. We're just trying to isolate, right? So now this is going to cancel out, and I got e to the negative 0.625t equals 1 over 199. Now I want to bring that variable down that's locked in the exponent, so I need logarithms, aka natural logarithms, because we got that nice base of e. This allows me to bring this down as a coefficient times ln of e, and ln of e is 1. So now I got negative 0.625t equal to ln of 1 over 199. And then the last step to isolate is I'm going to divide both sides by negative 0.625, and we're going to evaluate this to get an approximation in Desmos. And here we get roughly 8.469, which rounds to the nearest tenth to 8.5, which means it will take 8.5 days approximately. Boom, done. So for this question, we're meant to plot this in Desmos and see if it looks linear, exponential, or logarithmic. So let's do that now. So here, when we look at the graph of the data, look at how it makes this nice curve up, and then it shoots up. It increases more rapidly as we go to the right. And that's your classic exponential. So we will say exponential for the answer, boom, So first we need to find a formula for an exponential equation that goes through these 2 points, and then we have to express it as an equivalent equation with base e. So we're going to start with y equals ab to the x, and we're going to plug and chug. So first, I see that I have 0, 4 as my y-intercept. That immediately tells me that's my a value. And you can see when you plug in 0 for x, that goes to 1. So it makes sense. Now we have to figure out what b is, and that's why we have this nice second point. So I'm going to plug and chug. Y is 100 when x is -2. Now we're going to solve first by dividing both sides by 4. So I get 25 equals b to the -2. Now I can use a logarithm here to bring this exponent down, but really what this is saying is what value to the -2 is 25, or what value divided, 1 over that value squared is 25. So you can quickly isolate like this, multiply both sides by b squared while dividing by 25. So b squared equals 1 over 25. We take the square root of both sides, we get b equals 1/5. Now you might be saying, okay, well, b can also be -1/5, right? It's plus or minus, but a -1/5 in here wouldn't make sense with that point. So we're just going with the positive. So now I have y equals, and we said a was 4, right? So y equals 4 times 1/5 or 0.2 to the x power. And since I have it as 0.2 in the back of the book, let's rewrite this as 0.2. So now I need to represent this as an equivalent equation with base e. So we need 4 times 0.2 to the x equal to some coefficient a times e to the kx. Now I already know that a has to be 4. That's a given, right? We're not changing that original coefficient. So a is 4. So now we're really just trying to solve for this value of k. So again, I have variables locked up in the exponent. So we're going to start by taking the natural log of both sides. That allows me to bring this down, and ln of e is just 1. So now I have kx equals, and then bring this down as well, x times ln of 0.2. Now we can divide both sides by x, and look at that, k equals ln of 0.2. ln of 0.2 approximates to -1.60943, etc., etc. So if we rewrite this as y equals 4e to the -1.60943, and then we're going to round to 8 times x. So there it is. There is it with e as the base, and then here is it the original way that we solved it. Those are your 2 answers. Done. To solve this question, we need to figure out, first of all, what is 75% of the carrying capacity? And since this is a logistic function, the numerator is the carrying capacity. So what is 0.75 times 14,250? And when you plug it in to a calculator, you get 10,687.5. So we're trying to figure out for what value of little t will this equal this. Okay, so now let's isolate. We're going to start by multiplying both sides by the denominator. And why don't I simultaneously divide by 10,687.5? I don't want to distribute. I'm just trying to isolate the t. Now I got this nice situation. Now I'm going to subtract 1 from both sides. Then I have 29e to the -0.62t equaling this. And believe it or not, this simplifies really nicely to 4/3. 4/3 minus 1 is just 1/3. So look at that. Next, we're going to divide both sides by 29. And that's like multiplying by 1 over 29. 3 times 29 is 87. Now to bring this variable down, we're going to take the natural log of both sides. That allows me to bring this down, multiply by ln of e, which is 1. So now we get -0.62t equals ln of 1 over 87. And then my last step is I'm going to divide by that coefficient of -0.62. And to get this final value of t, we're going to plug it into Desmos. And then rounded to the nearest tenth would be 7.2. So we can say approximately 7.2 days for the win. Boom. Done. So for this question, first, we're going to plot the data in Desmos. We're going to look at it and we're going to say, what does this look like? Does this look like logistic? Does it look like exponential, logarithmic, whatever? And then we're going to run a regression to get a nice model for the data. So let's do that now. So as we plot this out, we get this function. Now, a typical logarithmic might go up like this, but this could still be a logarithmic just inverted, right? With a reflection across the y-axis. So I'm going to go with a logarithmic model. So here when we run it, these are the constants we get. And this is how you run a regression model in Desmos. So now let's copy this over. So as we mentioned, we're going with logarithmic and we get y equals this first constant. And they said rounded to 5 decimal places. They only give us 4 here, but this is what it would be if it's to 5 decimal places. And then it's minus that value because it's negative. And the 5th decimal would be 0 in this case. And then it's times ln of x. So this is how you do it. Boom. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.